Hello and welcome! Continuing my Repairathon today, I'll take a look at one board which I would be especially happy to fix if possible. The Super Socket 7 mainboard MSI MS-5169 version 4. Well, obviously this is an ATX mainboard designed for Socket 7 and Super Socket 7 CPUs like AMD K6-2 and 3. This board is based on the glorious ALI M1541 chipset. This board provides AGP, PCI and ISA slots, which make it a perfect candidate for a flexible DOS and early Windows 95-98 retro gaming PC. Unfortunately, this board looks like it went through some bad times. Let's see. First of all, the BIOS ROM was removed. The battery socket is broken and loose. There are a lot of heavily bent pins. This board was probably thrown a couple of times because some caps don't look too good anymore. Some are even visually damaged. Some caps leaked already and obviously have seen better days. They even feel loose. Oh, and on the back there is some heavy corrosion ongoing. This is probably due to some leaky battery from another board, I guess, but still this has to be treated. Yeah, and as you see, there is some broken solder joints indeed. Okay, and unfortunately I also see a very deep scratch here. It doesn't look good, to be honest. Also, someone has stolen the heat spreader from the voltage regulator, so it is now hanging in the air. I guess I will have to find a replacement for this one. On the parallel port, some pins are also slightly bent and a piece of plastic cover broke off, but it is nothing critical. And this is so far what I could find. Let's start. First of all the pins have to be straightened, primarily because I'll have to set the jumper somehow, but even more important to avoid that they touch each other and produce short circuits. And of course, we will need a BIOS ROM. Fortunately, on the retro web there are already all kinds of different BIOS dumps available. The board I have is a revision 4, so let's go with the latest better BIOS. And just as always, I used my TL866 programmer to write the BIOS onto the flash chip. Now it is time to set some jumpers. First of all, CPU voltage. I'm going to use a K6-2350 which requires 2.2 volts. So S2 on the second position has to be set. Now S1 header. It can be left completely open, which regarding to the tables on the PCB defaults to 100 MHz frontside bus and a multiplier of 3.5. Now the BIOS reset jumper to the no reset position. And of course the keyboard standby power on jumper. If you saw my video about the Asus P2B mainboard recently, you will remember what can happen if this jumper is left unpopulated. Okay, let's give it a try and see if it turns on at all. Now without a CPU, but let's add a post analyzer to see at least the voltage LEDs. Whoops, we have a short. The PSU went directly into protection mode and shut down. Oh, you know what? Even after a second, this transistor already feels slightly warm. Yeah, it's definitely a little bit warm. The other one is stone cold. Looking closely, I see also a little bit of burnt gunk underneath. I guess it is dead. Let's check for shorts. Let's put the ATX cable to see what we checked. First, 3.3 volts. It beeped first because the caps got charged and the current was flowing, so there is no short here. Another 3.3 volts. Ground is obviously beeping. 5 volt rail has no short. This is ground once again. 5 volts again, no short. Ground. Power good signal, no short. 5 volts standby, okay. 12 volts, no short. Okay, and here we seem to have a short. This must be another 5-volt rail. Yeah, those red cables are 5-volt rails. Yep, definitely shorted. Interestingly is that not all 5-volt rails are interconnected on this mainboard. Different rails obviously go to different circuits. Okay, white is -5 volts, no short, ground. Green cable is the switch and it is okay. Ground again, -12 volts and 3.3 volts again are fine. Yeah, these two 5-volt rails are obviously shorted. I think they go to those power transistors. 4 ohms look like a short for me. What about this one? Well, this looks shorted as well, but I'll have to remove them from the PCB first to check if the transistors are the culprit. Or maybe there is something else. I'll have to remove and replace the capacitors as well. Look at the corrosion underneath. Also looks like the traces are unfortunately heavily corroded as well. Let's use a fiberglass pencil and see what's under the solder mask and the corrosion. Well, doesn't look as bad as I was expecting. That's what I'd call luck, because these traces are incredibly dense and that would be quite hard to repair. The corrosion around the wires is also not as bad as I feared. But here is the reason why I really hate fiberglass pencils. Look at this, there are now glass needles all over the place. I hated getting them under the skin, it's really painful. That's why I prefer a Dremel polishing tool for such work. Now let's take a closer look at this ugly scratch. It looks to be really deep. This spot seems to be the worst. Let's check the continuity. Okay, we have continuity from the end to this point. And we have continuity from one end to another end as well. So the trace is not completely damaged. Lucky me. The next one, from one end to this point, is okay. Now end to end, okay as well. Wow, this one is also fine. Okay, I checked all the traces and it's hard to believe, but they all seem still to be intact. That is a relief, believe me. You don't want to repair traces which are so damp. Still, I'd like to polish away the soldering mask from the damaged spots and take a closer look once again. That doesn't look too bad. Maybe I should tin the traces later, but it's hard to believe that they survived that scratch. I also polished the other spots where the worst oxidation was and they all do look quite good. But look at the oxidation on the solder joints of the capacitors. If you have such rusty solder joints, I found it helpful to scratch them a little bit first with a pair of pliers. Or tweezers, because the oxidation will isolate the old solder and prevent it from joining with the fresh solder. This would make the desoldering quite annoying. After some scratching and with a little bit of flux, fresh solder would melt with the old solder and mostly decompose the oxidation. And again, removing the oxidation from the PCB using a polishing tool. Now, some of the electrolytic capacitors in this area are removed. Initially, I wanted to remove all of them, but I realized that I don't have enough replacement caps at hand, so for now I just removed the ones which looked worse. Later I'll have to reorder a pack of capacitors and recap the whole board completely. Now let's see if our short is still there. Yes, everything is still shorted, so it wasn't one of the capacitors. I guess it's time to get the transistors off the board. I will use a heat gun and I'd need to protect the plastic ATX power connector nearby. So I'll use a piece of cardboard covered with some Kapton tape. That should do the trick. And yes, this transistor is definitely bad. Let's see if the short on the mainboard is still there. Yes, this transistor is still shorted and has to be removed as well. But the good news is that on the pads of the old transistor there is no short anymore. Yay, and the short is gone. And both transistors are probably dead. So we have here two CEB603AL power and MOSFETs. Let's see what the tester says. Okay, it says that these are two resistors in a row, which is definitely wrong. And the other one shows similar garbage. I looked through my spare parts and couldn't find two 603 transistors, but I found a 703, which is very similar to 603. It is specified for slightly higher currents, but most of the other specs are the same. Let's see what the tester says about this one. Well, it detects an N MOSFET just as it should be. Now let's see what the tester says about the capacitors. Well, I'm surprised to see that the caps are still okay. The capacitance is at almost 1000 microfarads and the ESR is low. This one is also okay. This one has slightly higher ESR, but still okay. Oh, and this one is in perfect condition. Unbelievable. Now to the bigger ones. This one is obviously leaky and I'm pretty sure it has to be bad. Well, unknown or damaged part. As expected, this one is obviously dead. This one looks actually quite okay. It is clean, not bulgy. Let's see. Well, this one is obviously dead as well. And I have to recalibrate my tester once again. The calibration is actually only needed when testing the parts using a cable. And for calibration you have to connect all the probes together to test the cable resistance. I'll use a thick copper wire to make it a bit easier. Then you restart the device and press the button when it asks for the self-test. Now the probes have to be disconnected again and it calibrates the capacitance between the probes. As you see, we are in range of picofarads, so totally irrelevant when measuring capacitors around 1000 microfarads. But at least the tester should not complain anymore. Let's come back to the capacitors. The next is the one which got a dent on the top. This one could be also dead. And look at that, it's totally fine. Still, I would replace it since through a micro crack in the housing, the electrolyte could drip onto the PCB and damage it. So the verdict so far, two bad transistors and these two capacitors, which have to be replaced now. And if I will get this mainboard back to life, I'll order the other caps and replace them later as well. Digging through some boxes, I could find one working 603 transistor though, so this pair should be able to handle the job. As you see, I approached this repair highly unprepared, and have to improvise a little bit, but I think during the investigation it's totally fine to use some shortcuts. When you definitely found all the issues and culprits, you can order some good parts and do the final cleanup. But it's time to reassemble this mess. By the way, you don't need a heat gun to solder SMD transistors. To be honest, I even usually use a normal soldering iron for this work. First of all, I clean the pads from the oldest solder, then add some flux and fresh solder to the pads. Then I heat up the pads so the solder is fluid and put the transistor on it. The solder will cool down instantly, so it's not enough just to drop the transistor on top of it, but if you simply put the soldering iron on the heat spreader of the transistor, it will melt the solder underneath in a couple of seconds, since it is still quite hot. Then I use a pair of tweezers to align the transistor a bit and hold it in place. Afterwards, the pins can be soldered to the pads as well. And we have no shorts so far. Now the bigger caps. I have here some 1500 microfarad caps, which are actually new. I used them briefly for an experiment, that's why the legs are already trimmed, but well, these are low ESR 10 volt, 1500 microfarad caps, and they should do the job. Okay, everything is reassembled, the shorts are gone, and it's time for a test. .36 volts is definitely too much. The voltage is set to 2.2 volts. Maybe this is due to some missing load. Here I have a dead K62 CPU, which I could use for testing. Let's give it a try and see which voltage we'll get then. .63 volts, this is not good. I guess I will have to check the circuits once again. Okay, I don't know yet if following has something to do with the higher voltage, but you probably noticed my mistake already. I replaced two 603 transistors by one 703, which is very similar to a 603, and, as I thought, another 603 transistor. However, I misread the labeling, and it turned out to be a 6030 and not 603. I compared the datasheets and, well, the 6030 is, among other less important differences, a lot faster transistor than a 603 or 703. This could be an issue, since the controller switches those two transistors against each other. If one is open, the other one has to be closed. If both transistors would get opened, the circuit would end up in a short, connecting 5 volts rail directly to the ground. And if one of the transistors is a lot faster than the other one, it could theoretically happen that the slower transistor is not yet closed, where the faster one is already open. It depends on the used controller, but 26030 would be probably okay. However, a mix like this one is too risky in my opinion, so I will have to fix it. I don't want to use a heat gun again, because that would heat up the capacitors, which don't like that. That's why I'll use just a soldering iron to remove the transistors. Here I just go in reverse order. First desolder the legs, lifting them from the pads using a pair of tweezers. And then heat up the heat spreader of the transistor to melt down the solder underneath. Luckily, I could snatch another 703 transistor from my scrap parts, and it is even from the same manufacturer. Okay, time for another test. Still 2.36 volts, so the transistor was not the culprit here, but I'm still happy that I noticed my mistake eventually. Let's switch the voltage setting jumper a little bit and see if something changes. Interesting, the first two positions deliver the same voltage. The other settings deliver mostly 1.5 to 2 volts higher voltage than expected. Okay, let's take a closer look at how the voltage setting works on this mainboard. It is very similar on most mainboards of this age. There are these jumpers which can be used to select the required CPU voltage. Down here is the table of valid settings. For example, 2.2 volts is a set jumper at position 2. This is what I actually have currently set. From these jumpers there are traces which are going over to this IC. It is a DC-DC controller which controls the transistors, which I previously replaced, and maintains the CPU voltage at required level. Accidentally, the oxidized traces underneath are the ones which are going from the shown jumper header to the controller IC. I found a data sheet for the controller, and it has the VID0 through VID4 input pins which can be used to set up the voltage. Here is the table of settings which should correspond to our jumpers on the board. The VID signals are connected to 3.3 volts through a pull-up resistors, and the jumpers pull them to the ground, or 0 when set. So in this table, 0 means jumper set and 1 jumper is not set. So if looking at 2.2 volts setting, we see that all jumpers should be unset except the second one. This is exactly what I said previously. Now let's check the VID levels on the controller IC. VID 0 is low, but should be high. VID 1 is low, this is right. VID 2 is high, right. VID 3 is high, that's right. And VID 4 is also high. So there is something wrong with VID 0. The jumper is unset, but the signal is low. Let me remove all the jumpers. According to the table, everything should be 1 now, and the voltage should be at 2 volts. Yes, voltage is at 2 volts indeed. Yeah, and all the VID levels are high indeed. Actually, the circuit between the jumpers and the controller is that simple. They are basically connected to each other through a pull-up resistor. Here are the pull-up resistors, which are connected to this voltage regulator here on the one end, giving it 3.3 volts high signal. The other end goes to the jumpers and to the controller. If the jumper is set, the accordant signal is pulled to the ground or 0 volts. Here is what I found. The pin VID0 and VID1 on the controller seems to be shorted. I can measure the continuity between the accordant header pins as well as on the controller IC itself. So if I set the jumper to position 2, the position 1 gets grounded as well. With the other words, VID0 and VID1 are always both, either 1 or 0, so the controller is not correctly set up. Well, let me briefly summarize the next 30 minutes of useless work which I did. Obviously, the whole thing is really simple. There is a jumper, there is a pull-up resistor and the controller. No more, no less. One of those 3 things could be bad. Well, jumper itself can be obviously excluded. It is also unlikely that the resistor in such a circuit would be bad. However, the controller could get bad and misbehave. It is even quite often that the shorted power transistors can take out the controller or the other way around. So I decided to start with most obvious suspect and desoldered the controller IC. Unfortunately, the ATX connector was in the way, so I had to remove it temporarily as well. And to my surprise, the IC was okay, but I still had a short on the board. So I started to believe in impossible and removed the pull-up resistor network, which of course turned out to be okay as well. So without the IC and without the resistor, I still had a short on the board. And for me, it was a long way back to the very first lesson. How to shoot yourself in the foot and realize it 2 days later. I told you before that the oxidized traces on the back were accidentally the ones which were going from the voltage setting jumpers towards the DC-DC controller. Do you remember? Well, this was where I had to start over once again. Soldering with the camera in your face is not always an easy task, and as I soldered one of the capacitors, I accidentally touched some traces which were not covered in flux. Do you see this? Just compare this solder bridge to the size of the tip of my tweezers. It costed me half an hour of my life. Once the solder bridge was removed, the short on the VID0 and VID1 instantly disappeared. Now let's solder everything back in place and give it another go. And here we go, 2.2 volts as required, finally. Let me switch the jumper. Yeah, now all the voltages look right. Time to make a real ride. Here I have a K62350. Let's give it a go. The fan cable doesn't fit, but we don't need it for the first test anyway. The CPU voltage is fine and I can see some numbers on the post analyzer. Unfortunately, it doesn't give any beep codes regarding missing memory. Still, let's add some memory and see what happens then. And yay, numbers are running and we get some beep codes because of the missing graphics card. What a great success! Let's add a graphics card and keyboard and see if we get an image. Would you look at that? K62350 message is smiling from the screen. And the keyboard works as well. I can enter the bytes, but I think I'll turn off the system now because the voltage regulator with the missing heatsink gets really hot. Here I have some scrap where I can take a heatsink from. This one could fit, but the stands look to be too wide. Anyway, this one will hold the regulator cool for testing, and later I can find something what would be a better fit. So I desoldered it, and do you see, the stands are really too wide, so I will now not solder it but just screw the regulator with the thermal pad onto the heatsink. Let's also add the compact flash to IDE adapter with DOS and tools. Maybe these boards will be already able to boot into DOS, who knows. And of course we need another CPU cooler if we want to run some benchmarks. In the BIOS, IDE is set to auto-detect. I guess I'll leave everything at default values for now. And congratulations, we are in DOS, ladies and gentlemen, finally! Let's see, CPU identification says 350 MHz AMD K6-2, that's right so far. Just as usual on my channel, Doom is a good first test. .590 real ticks is a good result, but important is that it ran through completely. What does Quake benchmark says? .67.6 FPS. And again, important thing, it was stable. Superb! Well, the replaced MOSFETs are stone cold. That is a good sign, but I'll have to do more tests later. The 3.3 volts voltage regulator is hanging in the air with its heatsink, but at least it's not quite as hot anymore. Still, it is surprisingly warm, I have to admit. Well, this video is already being very long, and this board will need some more care. Besides of recapping, I'll have to replace the battery holder. It is broken, loose, and doesn't hold the battery in place. For the 3.3 volts voltage regulator, I'll need to find a better heatsink, which I could solder to the PCB. As you see, it is totally hanging in the air. On the back, I'll have to tin the traces, or at least cover them with some nail polish to protect them from oxidation. But all in all, this is a great board for a retro gaming PC. Not only is it ATX and would fit into a modern case, this board is highly flexible. With a K6 2 or 3 at 550 MHz combined with a, let's say, Voodoo 3 graphics card, this machine can be used to play games from 1999 or even 2000. And on the other hand, with reduced frontside bus and the multiplier and deactivated cache, this CPU can be throttled down to a slow 386 machine to play games from the mid to late 80s. With AGP, PCI and ISO slots, you get countless options for the retro hardware, exciting sound cards and many more. This is one of the best platforms for a retro PC of 90s hands down. And the best about this particular board is that it is back to life. And I hope you enjoyed this repair. Don't repeat my mistakes, let me do them for you. Please don't forget to leave your thumbs up or down if you didn't like it. And I say thank you and goodbye.